equation says that for a function which is going from D to R, domain is D and R is the range of that function f, which is defined as fx is equal to this thing, right? Where D and R denote the domain of f and the set of real numbers respectively, of course. R is the real number and D is the domain. If f is the surjective mapping, then the complete range of A is. Alright, so we are in options also, we can see from options that so the options have already told that A is going to lie between 0 and 1. We just need to look out for the inequality, right? Whether it is equal or not. Alright, so firstly we'll jot down whatever it is written in the question. So it is given that the fx is surjective. So what does surjective mean? Surjective means onto. Now what is the definition of onto? Onto function's definition says that for a function f to be onto, every y belonging to R must be attained by some x, right? So y just means the value of the function, whatever y is mapped to, it must be mapped basically. For example, this is the domain, this is the range, whatever the elements are there in the domain, they must be mapped to the certain value, right? No value in this box must remain empty, right? So let us say fx is y, right? So now we have to ensure that every y is having some value, right? We have to ensure that because we are given that the function is onto. So after substituting y, since we have to find what we mean by this thing that we need to ensure that y must be mapped. That means we need to find the range of y, right? That's how we'll ensure that every value of y is mapped. So let's see. So to find the range of y, we'll bring the equation in this form, right? So that we can apply further cases of discriminant, and that's how we'll find y. There is no option, right? Other than that, there is no option. All right. So there are two cases possible in that. This is a quadratic equation only if y is not equal to 1, right? And we'll solve for the next case also where y is equal to 1. So when y is not equal to 1, for a real x to exist, d must be greater than equal to 0. So if we have to ensure that the roots of this equation are real, right? Then d must be greater than equal to 0. Then we'll solve it, right? We'll further solve it till we get the equation, quadratic equation in terms of y, right? Now, we are saying that this equation must be greater than equal to 0 for all value of y which are real. Now, this quadratic equation is non-negative. So, for a quadratic equation to be non-negative, what is the condition? That is, discriminant must be less than equal to 0, right? So, we'll simply calculate the discriminant. Further, we'll calculate till we get a into a minus 1 is less than equal to 0. Then we'll plot the roots on number line and we see which is interval is of our use. Since it is negative, we'll we'll take negative interval. We'll finally get a belongs from 0 to 1 where both are included. Now for the next case where y is equal to 1, then equation is no more quadratic, right? It becomes a linear equation, right? Then equation 1 becomes this, minus 2x minus 2a is equal to 0 where x is equal to minus a. But wait a minute, does it lie in the domain? We cannot take every value of x which is there, right? We need to ensure it actually lies in the domain of the function. This means that f when x is equal to minus a must be valid, right? Must be valid. So recall fx is this thing, x square plus 2x plus a upon x square plus 4x plus 3. Okay. So this means that for this function to be valid at x is equal to minus a, the only problem which is giving to us is given by the denominator. Denominator must not become 0, right? Then only we'll ensure that fx is valid at x is equal to minus a. That means that minus a square plus 4 into minus a plus 3a cannot be equal to 0. That means a square minus a cannot be equal to 0, right? That means a into a minus 1 cannot be equal to 0. This means a cannot be equal to 0 or a cannot be equal to 1. Now, we'll name it as double star. So we had two conditions where we are saying that A belongs from 0 to 1 where both are included. But now we are contradicting a little bit that we are saying 0 and 1 are not involved. That means after taking the intersection of both the conditions, we finally arrive to a conclusion that A belongs from 0 to 1 where both are excluded. Okay. Now our work is still not done here. We need to check for the validity of fx at this boundary of A, right? Whether these things are also included. For example, if the option was not given to us in terms of 0 and 1, for example, one option could have been 0 till 3 or 0 till 2, then we have to further ensure that is it actually valid or not, or maybe some shorter interval that A belongs from 0 till 0.5, right? So right now the option is simple, so our work is done here, but we'll further check if fx is actually valid. So when A is 0, fx becomes x plus 2 by x plus 4. We'll put that in the original expression, then we'll get this, nothing difficult. Now we know that x cannot be equal to minus 4 and x also cannot be equal to 0. Because why we are saying that? Because we previously we found out that x is equal to minus a. So if a cannot be equal to 0, then x also cannot be equal to 0, right? So then we say that when a is equal to 0, fx is going to be this. And at x is equal to infinity, this function tends to 1. But do we know that y is equal to 1 is not actually achieved at a, right? It is not achieved. And similarly, when the next boundary condition a is equal to 1, we find this fx, right? And then similarly, when we put the x as infinity, using the concept of limits, we get that its value is 1, right? Because it makes infinity by infinity. Then y is equal to 1 is still not attained because it is just tending to it. It is not exactly 1, right? Tending does not mean equality. That means f is not surjective at the boundaries, right? So we proved that we by this thing we definitely proved it that we cannot take 0 and 1 because it is not surjective at that point because it is not included. So the final answer is D option.